Hello students, welcome to AskPrep. My name is Kadhavi. In today's class, we'll continue the further part of the structure of atom. Here, in today's class, we'll study about Heisenberg's uncertainty principle and furthermore concepts. So, Heisenberg stated that uncertainty principle is the dual behavior of matter and radiation. And he also stated that it is impossible to determine simultaneously the exact position and exact momentum of an electron. So, for an electron, you cannot determine where it is present and at what motion or at what movement it is moving in the rate of the speed and all, we cannot measure for an electron. And mathematically, he gave this in an equation as m delta v into delta x greater than or equal to h by 4 pi. So, delta p is given as m into delta v. So, he's substituting that in this equation as delta x, which is greater than or equal to h by 4 pi. And so, this is altogether taken as delta E. That is the energy or the uncertainty in energy into delta T with respect to time, that is uncertainty in time, is greater than or equal to h by 4 pi. Where delta E is the uncertainty in energy, delta T is uncertainty in time, delta P is uncertainty in momentum, and delta X is equal to uncertainty in position. Delta V is uncertainty in velocity. M is the mass of the particle and h is called the Planck's constant. And this uncertainty principle we can understand with the help of a very good example. Suppose if you are asked to measure the thickness of a paper with an unmarked meter stick. So you don't have meter to measure that. So obviously it will be inaccurate and meaningless. There will be not proper measurement provided. So to obtain the accuracy, what should we do? We should use an instrument with graduated scales. So that scales should be small than the thickness of the sheet of the paper. In the same way, in order to calibrate in the form of the dimension or the point charge. So therefore, point charge is not dimension, it is dimensionless. So we illuminate this electrode with the light or with an electromagnetic radiation, and so that the light emitted will have some wavelength. So we know the value of the wavelength or at what intervals the time taken by the electron to reach that certain point is smaller than the dimension of an electron. So in that way we can conclude that. So the next is significance. So how significant is uncertainty principle? It rules out the existence of definite paths or trajectories of electron. So how does it rule out the path of the electron? It doesn't always occur for an electron to move in the straight line, or it have to move in the curve, or it have to move in a rectangle form. Not like that way. It rules out this existence of moving in a straight line or example, a subatomic particle. Electron or proton or neutron, it is not possible simultaneously to determine the position and velocity at given instant of time or any degree of precision. And it is also not possible for the trajectory of an electron. So we cannot exactly determine how an electron moves in a definite path. It cannot be determined. And this Heisenberg uncertainty principle microscopic objects. So only microscopic objects like electron and all we can find, but not for macroscopic objects. So delta V into delta X, which is obtained, is much larger, and these uncertainties are real consequence. For example, mass of an electron is 9.11 into 10 power minus 31 kg. As electron is microscopic, this example holds good. And Bohr's orbit are fixed, and so it cannot hold good. Means the position and the momentum of the electron is replaced by the statement of probability. So, probability of electron moving in a definite or a stationary orbit may or may not be possible. This is called probability. So, you are expecting something which may be or may not be probable. Either electron can move, neither electron cannot move. So, this concept is explained by quantum mechanical model of an atom. So, the next concept is quantum mechanical model. So, Newton laws of motion was based upon the classical mechanics used this. So, motion of all the macroscopic. So, it failed to apply to microscopic objects like electrons, atoms, molecules, as these macroscopic objects can ignore the dual behavior of matter, that is particle and wave nature. But for microscopic objects, it has to undergo this phenomenon with the help of light and all. And as light possesses both wave and particle nature, this is primarily applicable for subatomic particles, and the uncertainty principle also was couldn't explain by the Newton's classical mechanics. So this branch of science which took into account this dual behavior of matter is called quantum mechanics. So quantum mechanics is a theoretical science which deals with the study of the motions of the microscopic objects which have both observable wave-like or particle-like properties. And it also shows the same property when it is applied to macroscopic objects to that of the classical mechanics. So what happened? This quantum mechanics was applicable to both microscopic and macroscopic objects also. This was given by Werner Heisenberg and Erwin Schrödinger in the year 1926, alone by Heisenberg. So then what are the important features of this quantum mechanical model? The energy of the electron in an atom is quantized. So quantization means it has some specific values. So energy of an electron always has some definite values. So when electron is revolving around the nucleus or it is bound to a nucleus, it has its own energy value. So that is why it is held to the nucleus tightly or very firmly. And the existence of quantized electronic energy level is a property of a wave, like a wave property of electrons, and it also follows the Schrödinger wave equation. And here, both the exact position and exact velocity of an electron in an atom cannot be determined simultaneously. So, exact position and exact velocity cannot be determined simultaneously. So, the path of an electron, hence, is a probability at different points. So, we can conclude that as it is probability, the path of the electron, it may be present in this point, it may be present in that point. It's a probability. And this atomic orbital psi is the wave function for an electron in an atom. For an electron, the atomic orbital is called the wave function. So if an electron is described by a wave function, we can say that the electrode occupies that function are possible for electron. There are many atomic orbitals in an atom, and one orbital always consists of two electrons. It may be s, p, one s orbital or one p orbital. It consists of only two electrons. So if there are multi electrons in an atom, how are the electrons filled in an atomic orbitals? So they are filled in the increasing order of their atomic energies. So therefore, orbital wave function psi is a characteristic of the orbital which it occupies. And the probability of finding the electron at a point within an atom is proportional to its square of the orbital wave function. And this psi square is known as the probability density and is always positive. And with the help of the psi square, we can predict the region of the nucleus where the electron might be. So the next one is the orbitals and the quantum numbers. These orbitals can be distinguished by their size, shape, and orientation. So if an orbital is of smaller size in the sense, there is a more chances of finding the electron near to the nucleus. And to determine the probability of finding the electron shape and orientation is not possible in all the directions. So as the electron size, shape, orientation is not possible in all the directions, a new concept called quantum numbers are introduced. So each orbital is designated by three quantum numbers. They are the n, l and m. That is, n is the principal quantum number, l is the azimuthal quantum number, n is the magnetic quantum number. Coming to the first quantum number, that is the principal quantum number, where n, that is called, it is a positive integer. Always principal quantum number is positive. With the value of n, that is 1, 2, 3, continues with respect to the number of atomic orbitals. And this principal quantum numbers which determines the size and to the large extent of the orbital. For hydrogen atom and hydrogen-like species, the energy and the size of the orbital, it depends upon n. This principal quantum number is also identified with the shell number. As the value of n increases, the principal quantum number is directly related. The number of shells also increases. The orbital increases, it is given by n square. Suppose if all the orbitals are of a given value of n, it constitutes a single shell of an atom. They are represented by the following letters: n is equals to 1, 2, 3, 4, and shell corresponding to K, L, M, N. So the starting a shell named as K, that is n is equals to 1, L, n is equals to 2, M, n is equals to 3, and 4, O, 5, like that. It increases with the alphabetical order along with the increasing numbering. The size also increases of the orbital with the increase in the principal quantum number. So as a result, the electrons move away or apart from the nucleus. As the energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with the increase in value of n. As the value of n increases, the energy of the orbital also increases. So the next concept is about azimuthal quantum number. It is also known as orbital angular momentum. It defines the three-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. So for a given value of n, the possible value of L are L is equals to 0, 1, 2 up to n minus 1. For example, when n is equals to 1, the value of L is also 0. When n is equals to 2, the value of L can be 0 and 1. If it is 3, the values are 0, 1 and 2. As each shell consists of one or more subshells or sublevels, so the number of subshells in a principal shell is equal to the value of n. For example, in the first shell, n is equals to 1, there is only one subshell which corresponds to L is equals to 0. So if there are two subshells, L is equals to 0, 1, and the second shell, n is equals to 2. So it determines the based upon the principal quantum number. So if it is n is equals to 1, L corresponds to 0. N is equals to 2, L corresponds to 0, 1. 0, if it is L is equals to or n is equals to 3, 0, 1, 2, and so on. And this each subshell is assigned an azimuthal quantum number, and the subshells corresponding to different values of L are represented by the following symbols. The value for L is 0, 1, 2, 3, 4, 5, corresponding to the number of subshells. If it is the value is 0, it is a subshell. 1, P, 2, D, 3, F, 4, G, H and 5. So these are the subshell notations. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. L is equals to 0, 0 in that way. So the next is magnetic quantum number. This gives the information about the spatial orientation of the orbital with respect to the set of coordinate axes. See, for any subshell which is defined by the L value, 2L plus 1 values of, so there it is, here L2L plus 1 ml values. ML is equals to, it corresponds to minus 1 to plus 1 or minus 2 to plus 2. Here it follows integer, but in principal quantum number only positive numbers. For L is equals to 0, ML value is equals to, we have to substitute in the above formula 2L plus 1. 2 into 0 plus 1 is equals to 1. So 1 s orbital. How many s orbitals are present? So for L is equals to 1, ML can be minus 1, 0 and plus 1. So 2 into plus 1 plus 1, that is 3. So 3p orbitals. For L is equals to 2, minus 2 minus 1, 0 plus 1 plus 2. 2 into 2 plus 1, that is 5. You get 5d orbitals. So these are the number of orbitals present in each subshell. So S has only one subshell, that is S. P has 3 orbitals, right? S has only one orbital. P subshell has 3 orbitals, Px, Py, Pz. d orbitals or 5. They have 5 d orbitals. So in that way. So it should be noted that the m derived from L values, they are all interconnected. Magnetic quantum number derived from azimuthal quantum number. Azimuthal quantum number is derived from principal quantum number. So for all the basis of this is the principal quantum number. So this each orbital in an atom is therefore defined by the set of values of n, l and ml, and this orbital described by the quantum number is n is equals to 2, l is equals to 1, ml is equals to 0 is an orbital in the phi subshell. So this example of l is equals to 1, ml is equals to 0 and n is equals to 2 corresponds to p subshell. So these are the following notations or the relation given between the subshell and the number of orbitals which is associated with it. Value of L 0, 1, 2, 3, 4, 5. Subshell notation S, P, D, F, G, H and the number of orbitals is 1, 3, 5, 7, 9 and 11. See, only these 3 quantum numbers are not enough to explain the spectrum of the multi-electron system. As in the spectrum you get a doublet, triplet, quadruplet and all. So, to predict the electron spin and all, another quantum number was proposed. So, in the year 1925, George Uhlenbeck and Samuel Goudsmit, they proposed the electron spin quantum number. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving around the Sun. How Sun revolves around the electron in the same way, how an electron revolves around this, how the planets revolve around the Sun, the same way electron revolves around the nucleus. Words, electron has charge and mass and the intrinsic spin angular quantum number is also present. The spin angular momentum of the electron is also called the vector quantity and it has 2 orientations with respect to a single axis. So that is the positive and the negative. It is the plus half or the minus half spin quantum numbers, that is ms. And these are called the 2 spin states of the electron and they are represented by 2 arrows. One is the spin up arrow and spin down arrow. 2 electrons that have different ms values, one the plus half and the other minus half, they are said to have opposite spin orbital and it cannot hold more than 2 electrons. And these 2 electrons should have opposite spins. And what is the conclusion of these quantum numbers? So, N is the shell. It defines the shell. And it also determines the size of the orbital and to the large extent of the energy of the orbital. There are N subshells. And thus L identifies the subshell and it also determines the shape of the orbital. There are 2L plus 1 orbitals of each type in a subshell. That is 1s orbital, that is L is equals to 0. 3p orbitals, L is equals to L, 1. 5d orbitals, L is equals to 2 per subshell. And to some extent, L also determines the energy of the orbital. And ML determines the orientation. Whereas ML has 2L plus 1 values, which is same as the number of orbitals per subshell. So which means the number of orbitals which is equal to the number of ways in which they are oriented. And ms is the orientation of the spin number of the electron. Shapes of the atomic orbital. So as there are 4 different shapes of the orbitals, there are 4 different primary orbitals, s, p, d and f with different shapes. And out of the 4, S and P are most considered because they are most common in all the organic and the biological chemistry. S is spherical shape with the nucleus at the center. P is dumbbell shape and P is a double dumbbell shape, a clover leaf shape. And these orbitals in an atom are organized in different layers or electron shell. See, according to quantum atomic model, an atom can have many possible number of orbitals. And these orbitals are classified on the basis of their shape, size or orientation. And smaller the size of the orbital means there is a chance of getting an electron near the nucleus. See, the shape of the s orbital. It is spherical. It consists of x, y, z axes. And the boundary surface diagram is given in this way. It is a 2-dimensional figure. These s orbitals are spherical. They have the probability of finding the electron is equal in all the distances. That is, it is spherical. Wherever you put an axis, it reaches the same point of the other half or the other side. So as the principal quantum number value increases, that is n, the size of the s orbital also increases. 4s is greater than 3s is greater than 2s is greater than 1s. Shape of the p orbital. It is the dumbbell shape with 2 lobes on either side of the plane passing in between the nucleus. The 3 p orbitals are differing with respect to their direction of their axes in respect to side shape and energy. As they lie the respective directions, they are named with px, py and pz. And they are mutually perpendicular. All these 3 orbitals, p orbitals are mutually perpendicular. Similar with the s orbital, as the size increases, the energy also increases with the increase in the principal quantum number. That is 4p greater than 3p greater than 2p. Shape of the d orbital. So the magnetic quantum number is for the d orbital is given by -2, -1, 0, 1 and 2. So as a conclusion, we can say there are 5 d orbitals. So each orbital is different from one another with respect to their xy axes. dxy, dyz, dxz, dx square minus y square and dz square. See, out of these first 5 d orbitals, the 4 d orbitals are similar to each other, which is that are different from the dz square, and the energies of polar d orbitals are same. So we can see the orientation of the different d orbitals. The next one is the energies of orbitals. The energies of the orbital is given below as 1s is less than 2s, which is equal to 2p, less than 3s, 3p, 3d. The shape of the 2s and 2p are different, but the electron has the same energy as it is present in the 2s orbital. They possess the same energy. And if the orbital possesses the same energy, they are called degenerate orbitals. So 1s orbital in hydrogen atom is the most stable condition and it is called the ground state. And this is held together by the electron in the orbital, which is held together. And the electron in the 2s, 2p or higher orbitals in the hydrogen atom is in the excited state. So we can see here in the figure it is given as 1s, 2s, 2p. So this is for the hydrogen atoms, energy level diagram. This is for the multi-electron. But here for multi-electron, the energy depends on principal quantum number and also azimuthal quantum number, as all the orbitals have different energies with respect to number of electrons. So the main reason for having different energies of the subshell is the mutual repulsion among the electrons in the multi-electron. So in the the mutual repulsion is caused due to the multi-electrons present. And in hydrogen atom, the attraction between the negatively charged electron and the positively charged nucleus is present. So beside the presence of attraction between the electron and the nucleus, there is a repulsion between every electron and other electron which is present in the atom. And this stability of an electron in multi-electron is due to the attractive interactions are more than the repulsive interactions. So the next concept is about effective nuclear charge. So the interaction of the electrons in the outer shell with the electrons in the inner shell are very important. So on the other hand, the attractive interaction of the electron, it increases the increase in the positive charge. So due to the presence of the electrons in the inner shell, the outer shell electrons will start repelling the innermost shell electrons. This is called the screening or the partial screening of the positive charge on the nucleus by the inner shell electrons. The net positive charge which is experienced by the outer electrons is known as effective nuclear charge. So as the shielding of the electrons is done by the inner electron, shielding of the nucleus done by the inner shell electrons, the attractive force which is experienced by the outer shell electrons increases with the increase of the nuclear charge. The energy of the interaction between the nucleus and the electron decreases and it increases with the increase of atomic number. Both the attractive and repulsive interaction depends upon the shell and the shape of the orbital in which it is present. Suppose if an electron is spherical, S orbital shields the outer electrons from the nucleus more effectively as compared to the electrons present in p orbital. Similarly, p electrons shield the outer electrons more efficiently than the d orbitals, even though they are present in the same shell. So, for a given shell, the effective nuclear charge which is experienced by the electron decreases with the increase of the azimuthal quantum number. That is, the s orbital electron will be bound more tightly to the nucleus than the p orbital electron. Than the d orbital electron, p will be more tightly bound. The energy of this orbital will be lower. It is more negative than that of p orbital, which has less energy than that of d orbital. And the extent of shielding from the nucleus is different for electrons in different orbitals. And it leads to the splitting of the energy levels within the same shell and with the increase in the energy of the orbital. If the value of n plus L for an orbital is lower, it has lower energy. and the energy is also decreases within the same shell with an increase in the atomic number. The energy of the 2s orbital of hydrogen is greater than the 2s orbital of lithium, and 2s orbital of lithium is greater than that of sodium. So it continues in the order of hydrogen, lithium, sodium, potassium, like that. Filling of the orbitals. So this filling of the orbitals takes place with the help of the Aufbau principle. And this Aufbau means building up in German. So building up means filling up of orbitals with electrons. The principle states that in the ground state of the atoms, the orbitals are filled in order of their increasing energies. The electrons first occupy the lowest energy orbital and then enter into the higher energy after the filling of the lower energy. So 1s, 2s, 2p, 3s, 3d, 4s, 3d, 4p, 5s, 4d, 5p, 4f, 5d, 6d, 7s. This is the order. After completing 1s, it enters to 2s, 2s after 2s, 2p, 2p, 3s, 3p, 4s. The filling of the orbitals, and it fills according to this. We have to fill the orbitals according to this. Valence electron in potassium, for example, must choose between 3d and 4s orbitals as predicted, but this is found in 4s. So in many cases, it may be vary due to the structure or the change in the energy levels. A slight variation is observed, but majority this rule is followed. So the next one is about Pauli's exclusion principle. And the number of electrons is to be filled in various orbitals is restricted by the exclusion principle given by Pauli. So 2 electrons in an atom can have same set of 4 quantum numbers. In an atom, 2 electrons can have same set of 4 quantum numbers. And only 2 electrons exist in the orbital, and these electrons must have opposite spin. They may possess the same quantum numbers, that is principal quantum number, azimuthal quantum number, and magnetic quantum number, but the spin quantum number should be different. That is, one is positive, one is negative, one is opposite spin. And the number of electrons occupied in an orbital is depending upon the capacity of the electrons which is present in the subshell. So for 1s subshell, it consists of only one orbital, and the maximum number of electron occupancy is 2. For example, in P and D subshell, the number of electrons can be 6 and 10 and so on. So this is summed as the maximum number of electrons in the shell with the principal quantum number n is equal. The Hund's rule of maximum multiplicity. So this rule deals with the filling of orbitals which is belonging to the same subshell. That is the orbitals of equal energy, which is called degenerate orbitals. It states that pairing of electrons in the orbitals belonging to the same subshell, that is P, F or D, which do not take place until each orbital belonging to that subshell has one electron that is singly occupied. There are 3p, 5d and 7f orbitals. Therefore, the pairing of electrons will start in P, D and F with the entry of 4, 6 and 8th electron. Similarly, it is observed that a half-filled and fully filled degenerate orbitals, they acquire extra stability due to their filling of electrons previously. Electronic configuration. This is called the distribution of electrons into the orbitals of an atom is called electronic configuration. The electronic configuration is represented in two ways. For example, SA, PD, DC notation. It is S1, P1, D1 in that way. Subshell is represented by the letter symbol, and the number of electrons is represented by the superscript A, B, C, D. And the orbital diagram, this is the second type of representing the electronic configuration, and the subshell is represented by the box with indicating an arrow with a positive spin or a negative spin. And this orbital diagram helps in representing all the four quantum numbers. The hydrogen has only one electron. It is the orbital with the lowest energy, the 1s orbital, and it is 1s swap. Means it has only one electron in the 1s orbital. The second is the helium. It is 1s2, as it has two electrons in the 1s orbitals. So, in the same way, it is mentioned here the electronic configuration from sodium to argon has written as Na, Ne3s1, argon, neon, 3s2, 3p6 in that way. The stability of completely filled and half-filled orbitals. Ground state electronic configuration is always the most stable orbital, and certain elements such as copper or chromium have two subshells which differ in their energies, but the electron shifts to a subshell of lower energy from higher energy. So this shift results in the orbitals of higher energy also getting completely or half-filled orbitals. So the valence electronic configuration of chromium and copper is therefore is 3d5 4s1 and 3d10 4s1 respectively, and not 3d4 4s2 and 3d9 4s2. So there is an extra stability associated with these electronic configurations. So this is the symmetrical distribution of electrons. Electrons in the same shell had equal energy, but the spatial distribution is different, and the shielding of one another is small, and the electrons are attracted more to the nucleus. And exchange in energy. These two or more electrons have the same spin and are present in the degenerate orbitals of a subshell. These electrons tend to exchange their position, and the energy is released due to the exchange is called exchange energy. So if the exchange is more, it takes place as maximum, and the subshell is either half filled or completely filled. As a result, as the energy is maximum, so the stability is also maximum, and this exchange of energy is based on Hund's rule that electrons which enter the orbitals of equal energy have parallel spins as far as possible. In other words, the extra stability of half-filled and completely filled subshell is due to relatively small shielding or smaller Coulombic repulsion energy and larger exchange energy. So thank you everyone. If you have any doubts, feel free to comment below or email us from AskPrep. Thank you.